So now we're going to get started with part two of module two, which deals with pressure distribution in a fluid. And we're going to continue this module by starting with an example problem. So the example problem is already written out, so I invite you to copy it down if you want to. It'll be available in your notes as well. But the example problem says a lake has a depth of 60 meters and atmospheric pressure is 91 kilopascals. Estimate the absolute pressure at maximum depth. So how do we go about solving this problem? So we're going to be using the equation that was written out for us a little bit earlier and that we derived in the previous section. But before we even get started, let's draw a little bit of a diagram of what's happening and what is happening. So I want us to draw the actual lake and how it works. So we have a lake bed. And we're told that the lake has a depth of 60 meters. So we know that there's a depth of 60 meters of this lake, okay? It has sort of a height of 60 meters. And the surface of the water is 60 meters above the bottom of the lake. And above this water, so water we can usually define as like this little symbol here that I'm drawing. So you usually can define water as with this little symbol. And above this water, we have air. So we can say air, we can say there's water here in the lake, and anything above here would be air. So anything above this surface would be air. And this is what we call the free surface. So this is called a free surface. Okay, it's the surface at the top of the water. And we're told that at that we have an atmospheric pressure of 91 kilopascals. So pressure atmospheric is equal to 91 kilopascals. That means that at this free surface, we actually have 91 kilopascals of pressure. So if we put a little 1 here and a little number 2 to determine our 2 points in our system, we can say the pressure at 1 is equal to 91 kilopascals. Because at the surface, the pressure of the water is equal to the pressure of the air. And we can go even a little bit further and say that the free surface is where z is equal to 0. Okay, remember we always say z is positive in the upwards direction. So negative z would be the direction of gravity. So we can say that gravity is essentially going in this direction. Okay, there's gravity acting upon the water and the air as well. So with this information, we can find what we're trying to find is pressure 2. Okay, so we're trying to find pressure 2. That's our goal. That's the absolute pressure at maximum depth. So going from there, how do we start the problem? Well, we start with our equation, P2 minus P1 is equal to minus gamma that we derived for elemental fluids in the direction of gravity, as well as we know that the fluid is pretty much static in the lake. We're not told anything about velocity of the fluid or anything like that. And it's going to be z2 minus z1. So that's the equation, okay? And remember that in our equation, this gamma is equal to rho g. And this is going to become important because we're going to look at two different ways of evaluating these equations, essentially. Two different ways of figuring out how to evaluate for a specific weight. Okay, so the first thing we have to do is figure out what are the different values of z. So if z is equal to 0 at the surface, so we said the free surface z is equal to 0, then it would make sense that since z is positive in the upper direction, it means that z2, or the height at point 2, is minus 60 meters. So we can plug in already what we have in terms of our data. We have the following data. So we can say that pressure 2 minus 91,000 pascals and notice how I changed from kilopascals to pascals to keep it all in SI units for now, is equal to minus gamma multiplied by Z2, which is minus 60. Okay, and be careful with the signs here. You want to keep all the signs correct. Minus 0, which is Z1. Okay, so we have this equation. And the last piece of the equation that we have to find is specific weight. Now, there's two ways to find specific weight. The first way, and this is a pretty limited table with different values, but the first way to find specific weight is to say, let's look at table 2.1 in our textbook, which is also available in your handout, and find out that the specific weight is equal to 9,790 newtons per meter cubed at 20 degrees Celsius. So it's pretty close to what we're at. We're not really told the temperature or anything like that. So we can go with it and we can use that equation. So one way to do it is to use table 2.1 and say specific weight, let me write it in white, specific weight is equal to 9,790 newtons per meter cubed. Now there's another way to do it too, and it's to say that specific weight is equal to rho g, okay? And we know what g is, and we can go find rho in appendix of our textbook, which is appendix A3. And in your in your in your handouts for this chapter, you also have access to the appendices of the textbook. So I have copied the appendices of the textbook in this module. So you'll be able to see that as well. So if we go to appendix A3, we actually see that we can go to, so the appendix looks something like this. We have physical properties of fluids in appendix A. And if we go to A3, which would be on page 811, we see that there's a bunch of different liquids here, and we're told that these are the properties of common liquids at 1 atmosphere and 20 degrees Celsius. And we see that water has 998 kilograms per meter cubed. So we could use this technique as well. So what we would do here is we would say, okay, density is equal to 998, and we would multiply by 9.81, which is our gravity. And we get a value of 9790.38. So very, very close, okay? Now, in our problem, we're going to be using the first value because I think it's easier to find and you do one less calculation, but you could also use rho g and find it that way. Okay, two different ways of finding it. And then it's just about doing the calculation and figuring out what the pressure is. Now, we also know that at a higher depth, the pressure is going to be higher. So if your calculation yields you a pressure that's going to be lower, there's something wrong with your calculation. So we can say that P2, by rearranging the equation, P2 is equal to minus 9790 multiplied by minus 60. Sorry about that. Minus 60 plus 91,000. And we finally get that P2 is equal to 678,400 pascals. Or, in other words, 678.4 kilopascals if we want to bring it back to kilopascals. And that's essentially our first example problem that we've done in the class. Now, the next thing I want to talk about is a little bit of how we measure pressure with different instruments throughout the class. So the first one is the mercury barometer. And the barometer is a way to measure pressure that's pretty interesting. And we already talked about it a little bit earlier in the first part, but let's talk about it again here. So I'm going to copy over a figure from our handout. Just bear with me for a second. And what the mercury barometer is essentially an upside down test tube inside of a bowl, and we add some mercury. And what we do to this is we create an area here where we have P1 is equal to 0. So it's essentially empty. It's as if it was a vacuum. Okay, so we create a vacuum in here. And by creating a vacuum in here, we get sort of some suction for the mercury. And the mercury is going to reach a certain level. Now, the certain level that the mercury is going to reach is going to allow us to read for for atmospheric pressure that day. So this is a way to read pressure atmospheric for the specific day. Okay, so we know in our system that the pressure at the top here is equal to 0. So I don't know why this is happening. We know that the pressure at the top, P1, is equal to 0. So we can call this point 1. And point 2 can be defined as this point right here. So this is going to be point 2 in our system. Now, we know that at point 2, we have pressure atmospheric. It's directly connected to the atmosphere, and we're told in the little diagram here that we have pressure atmosphere. And now what we need to do is we need to figure out what the pressure is from the mercury. Okay, so what we can do is we can use the same equation. We can say P2 minus P1 is equal to minus gamma times Z2 minus Z1. And by simplifying the equation, we can also say that the height at point 2, so if we look at the height right here at point 2, is equal to 0. Okay, that's going to be our 0 height. And then Z1 is equal to H. So we can say that Z2 is equal to 0, and this being positive, upwards being positive, we can say that Z1 is equal to H, as illustrated in the diagram. And from there, we can plug in the values. So we have P atmosphere minus 0 is equal to minus the the specific weight of mercury. Okay, so that's the specific weight of the liquid that has a height difference, multiplied by 0 minus H. Okay, point 1 is negative H. And if we rearrange this equation, so we have a negative here and a negative here, if we rearrange this equation, we can see that height is equal to P atmosphere over the specific weight of mercury. And we know that at standard sea level, usually our P atmosphere at standard sea level is usually equal to, P atmosphere is equal to 101,325 pascals. And we also know that the specific weight of mercury, which can be found in table 2.1, we have mercury here at the bottom, is equal to 133,100 newtons per meters cubed. And so if we plug into this equation, we get a height of mercury of 0.761 meters, which can be rewritten as 761 millimeters. And this is how we would measure the atmospheric pressure. Now, on a certain day, the atmospheric pressure can vary from this this standard 101.325. So if we have this mercury barometer and we now have, today we measure a height of 750, we can now plug in 750 in that equation, multiply it by the density and the gravity of mercury, or the specific weight of mercury, and get a pressure atmospheric for that day. So it's a pretty useful tool to measure atmospheric pressure on any day, thanks to just the height of the column of mercury. Very easy to do. Now, moving forward from this, what I want to do next is to look at hydrostatic pressures in gases. So we looked at pressures in liquids. Now let's look at pressures in hydrostatic pressures in gases. So gas is not like a liquid, and gases usually have, if you have a large pressure change, you actually have a change in density. So if you have large pressure differences in gases, you get a change in density. And that means that density is variable, okay? So if we go to our ideal gas equation, we know that P is equal to rho times RT, okay? That's our ideal gas equation. So the goal from the ideal gas equation is we can find density. So with the ideal gas equation, we can find density at a given pressure and temperature. So if we have a given temperature and pressure, we can find what the density is. And with large variations in pressure, we might have some different densities within our gases. So we can't just assume that our gas is going to be always the same density, which is something that we can assume for liquids. Okay, so we would just rearrange this equation to say rho is equal to P over RT, and we can find that. Now, if we go back to our gravity equation in its simplest form, we had dP dz is equal to minus rho g, okay, if we remember that. And so now what we can do is, since we came up with an equation for rho using the ideal gas equation, we can substitute the ideal gas equivalent. So we can substitute the equation on the left here into, so we can substitute this and bring it into this equation right here. And so we get that this is equal to minus P over RT times G. Now, we can go a little bit further with this, and we can say, all right, this is our fundamental equation that we derived earlier. We now have substituted the ideal gas equation. What if we were now to rearrange it and integrate it? So what we can do is we can bring all the pressures on the left side. So we can say dP over P. So we're bringing the pressure term on the left side. And then on the right, we're going to leave all the other terms. So we're going to have, sorry, not, I'll put this in a second, but we're going to have minus G over RT times dz. Okay, so we just rearranged the equation a little bit. And now we're going to integrate both sides of this equation. We're going to integrate both sides to get an explicit solution for the problem. So by integrating, what do we get? So we're going to integrate from 1 to 2 and from 1 to 2. So on the left side, we're going to get the integral from 1 to 2 dP over P is equal to, and you should know how to do this, but I'll give you the answer here, is equal to ln P2 over P1. Okay, we're using laws of natural logarithms to figure out that ln P2 over P1 would be the solution here on the left side. On the right side, we can leave it for now as an integral but we can simplify our top integral a little bit. We know that gravity and the gas constant are constant. So we're going to take those out of the bracket. So we have minus g over r times the integral from 1 to 2 of dz over t. Okay, so that's the simplest form of the equation that we can have, would be this so far. Now, in order to simplify it further, we need to make a further assumption. So let's make an assumption that temperature does not change. So let's assume that in the atmosphere, between two points in the air or in the lower atmosphere, let's say there's going to be no change in temperature. That might not be correct all the time, but let's assume it in this case. Okay, so it does not change. So what we can do now is we can say, we can simplify the equation and run through the integral now with t outside of the integral. And we're going to say that t is equal to T0, okay? And T0 just means the atmospheric temperature. Okay, so when we assume that temperature does not change, we rename T as T0. And for fluid mechanics people, it means that this is the atmospheric temperature. Okay, so we now have ln of P2 over P1 is equal to minus G times Z2 minus Z1, now that the integral is alone, divided by R T0. And we can simplify it a little bit further by bringing the natural logarithm to the right side. So we can have P2 over P1 is equal to the exponent, or e to the power of, it's the same thing, of minus G times Z2 minus Z1 over R T0. And if we do have varying temperature, so this would be the equation that we would use for change in pressure as a function of height in air or in any gas. Okay, so we have the gas constant, we need to know the temperature. If we know gravity, we can then figure out, with the height difference, we can figure out our change in pressure. Now, if we do have a varying temperature, we can use another relationship that will allow us to work with varying temperatures. Those relations are in your textbook, and we won't write them out for now because we don't really need them for anything, but they are in your textbook if you want to. I will write them out right here, but I'm not going to explain them in detail. But essentially, there are some relations for varying temperatures which are found from experimental data and figuring out some constants that are used for most cases, essentially. So for varying temperature, we have the following formulas. P is equal to P atmosphere, and this is a mix of theory and experimental data, minus B times Z over T0 to the power of G over RB. Okay, so this is a power. And G over RB is just a constant usually, and this constant is equal to 5.26 for air. So it has a different constant for every fluid, but for air it's 5.26, for every gas, I mean. And we also have a term that is density is equal to density 0, which is our atmospheric density, okay, it's our standard density, of 1 minus Bz over T0 to the power of G over RB minus 1. Okay, once again, a power. And you can see that these are essentially just ways to figure out what's happening and rearranging the equations. So you can convert the equation from pressure to density by doing some mathematical tricks. But essentially, just to give you the constants here, rho 0 is equal to 1.225. P0 is equal to 101,325. So again, atmospheric. And then B is equal to the lapse rate. It's called the lapse rate. And again, we're not going to go into detail on this, but it's just for your information, is equal to 0.0650 Kelvin per meters. Okay, so these are ways to figure out what the pressure would be at a certain level based on varying temperatures. Okay, so I don't believe we'll do an example on this, but this is just for your information in case you're interested in varying temperatures. And yeah. Okay, so going back to our study of measurement and going back to some other measuring tools that we have, another measuring tool that we have for pressure is to use a simple manometer. And once again, I'm going to use one of the figures that we have in our handout that you have access to as well. And I'm going to copy it over under here. So this is a simple manometer. And what this simple manometer does is it measures the gauge pressure relative to atmosphere. And if we look at this, we can see a few different things. So it's going to measure the gauge pressure relative to atmosphere. So we see a few annotations already in our simple manometer, but let's try and understand what's happening here. So essentially, we have some sort of gas. So we have some sort of gas in tank A. So we have some sort of gas in tank A, and then on the other side of this tank, we have pressure atmosphere. Okay, so on this side, we have pressure atmospheric. On the left side, we have a pressure A at this level. So we have a pressure A at a level called ZA. Okay, and we have a fluid that is placed between between gas A and the atmosphere, which would have air. Okay, and how this works is we're going to have a little bit of a technique that we're going to use here. So what we're trying to find is the difference between pressure A and pressure atmosphere. Okay, and pressure atmosphere is actually P2. So we're going to call P2 pressure atmosphere. Okay, and it's at this level. So we're trying to find the difference in pressure at A with the difference in pressure in the atmosphere. Okay, so our goal is to find PA minus P2. Okay, we're trying to find the gauge pressure relative to the atmosphere. Okay, so how is it going to work? How are we going to work out this problem? Well, we're going to break it up into two different parts. Okay, we have two different parts to our system. The first part of our system is trying to figure out what the pressure difference between and I'll write it in orange, between this point here and our pressure A. Okay, so we have to find the difference between that point and pressure A. So the first thing we're going to do is we're going to say, all right, we know that pressure at A and pressure at point 1, okay, so this is actually pressure 1, labeled as pressure 1. We know that pressure A and pressure 1 are different, okay, and we can calculate how they are different by the equation that we derived earlier. And we can also know that now we have this fluid that is running continuously from here all the way to here. We know this fluid is running continuously, and we remember the fact that if there's a difference in height in a fluid, that means that there's a difference in pressure in that fluid. And we know that essentially the difference in pressure between, so the next step we're going to do is find the difference in pressure between, so let me erase a little bit of the stuff, the difference in pressure between this point here and this point here, where the pressure atmospheric is. So the next step is to find the pressure, the difference between the pressure 1 minus the difference between pressure 2. And we can find that. It's one fluid, right? So we have, this is fluid A, okay, or gas A, and then this is fluid 2. Okay, so we have two different systems that we're going to put together. Now, in order to find the difference in pressure between A and 2, we actually can combine these two equations together. So we can say that PA minus P2 is equal to, and we're going to go from left to right. So we just go from left to right and we try and solve the problem that way. So we have pressure A is at a different height than pressure 1, so it's going to change. So PA minus P1 is going to be a difference. And then, so this is our first part. And then if we continue going towards the right, we know that pressure 1 and pressure 2 have a pressure difference. And if we add those two together, so pressure 1 minus pressure 2 have another difference. And if we add those two together, we actually see that pressure 1 would essentially cancel. Okay, so that makes sense. It would cancel. Now, we're actually not going to make them cancel, because if not, we can't find PA minus P2. We're actually going to write out the expressions of PA minus P1 and P1 minus P2 in terms of the heights, so that we can figure out what's happening, so that we can actually figure out the difference in pressure between A and 2. Okay, hopefully this makes sense. If it doesn't make sense, it'll make sense as we go along and do more example problems. Okay, so the liquid is essentially separating the two gases together. And if we think about it, a manometer is very simple. You have a system that looks like this, okay, connected like this. If the liquid level on one side is lower than the other, we know that the pressure at A is greater than P atmospheric. Okay, if the liquid level is lower at this point, then we know that the pressure atmospheric would be greater than PA. Okay, so a pretty neat way of doing it. Okay, so let's go back to the problem. So now what we can say, instead of canceling out the P1s and then being left with PA minus P2 is equal to PA minus P2, we can actually say that this is equal to, so now PA minus P2 is equal to minus gamma A, okay, that's fluid A, times ZA minus Z1 minus gamma two. So actually I'm going to call this fluid B. I guess it makes more sense. I'm trying to think. No, let's put it as fluid 2. So gamma 2 is equal to Z1 minus Z2. So this is fluid 2, which is our liquid. Okay, and now we have this equation here. So now what we can do is we can write out the whole equation. So PA minus P2. So what I can do now is I can say, let's rearrange this to try and rearrange this from with PA with everything on one side and everything being equal to atmospheric. So you would be left with, and we can also talk about what we can also change the specific weight to density and gravity, okay, if we want to. So fluid A, so let's bring everything to one side. So PA plus this term here is going to go to the left, plus specific gravity A, which is also equal to rho of 1 times G. So if we look up here, we are told that this is rho 1, okay? So we have rho 1 as our density. So rho 1G times ZA minus Z1, and then plus gamma 2, which would also be equal to rho 2G if we wanted to, times Z1 minus Z2. Okay, and that's equal to pressure 2, which is equal to pressure atmospheric. Okay, we're told that in the question. Okay, so this is the definition of essentially Pascal's law. So this defines what Pascal's law is. And this helps us understand what Pascal's law is. Pascal's law says that any 2 points at the same elevation, so any 2 points at the same elevation will be at the same pressure. And that makes sense, right? If ZA minus Z1 would be equal to 0, so if we look at this first term right here, if the height difference would be 0, this term would disappear. If the height difference would be 0 in this one, this term would disappear and we would just have PA is equal to P0. But because we have a difference in height, PA changes. So the next thing I want to do is I want to do an example of this and really try and understand what's going on and really go through the problem with you as if we were doing it together. Okay, it is a video and it is different than being in person, but hopefully you'll be able to follow my logic and understand my logic of thinking while I'm doing the problem. So what I'm going to do now is I'm going to copy over a problem again from your figures. So it's the next problem in your figures. And you can attempt to do this by yourself if you want to, but I would listen to the lecture first and then try and do it by yourself after. And there are some problems in your study problems which will help you do these as well. So just try to do it with me in this first instance. So we have pressure gauge B is to measure the pressure at point A in the water flow. If the pressure B is 87 kilopascals, estimate the pressure at A in kilopascals and assume all fluids are at 20 degrees and see figure E 2.4. So we see that we have 3 different fluids. So we have SAE30 oil, that's the first thing. Then we have a second fluid of mercury, and then we have a third fluid that is water, and it's water flowing. Okay, so we have 3 fluids. So the first thing we're going to do is sketch a diagram. Okay, so if you didn't have a diagram of your system, the first thing you would do is sketch a diagram, which is already sort of done for you. But we're going to add to this diagram. Now, the second thing we're going to do is we're going to assume that this is a static problem. Even though we have water flowing, we're not told that anything is moving within our system, so it's a static problem. Everything is fixed. Okay, and the third thing we're going to do is we're going to find property values. We know we're going to have to use property values for SAE 30, for mercury, and for water. So let's write them down. So we can go to table 2.1, which is above in this lecture and in your handout, and we can write that gamma of water, which we had written earlier, is equal to 9790, and we can say that gamma of mercury is equal to 133,100, and we can say that gamma of oil is equal to 8720. And again, this is pulled out of our table 2.1, which is available in your handout. Okay, so we have these three values. So how do we get started with this problem? Well, the first thing we're going to do is we're going to define height 0. Okay, so what the first thing I'm going to do is I'm going to say the bottom here for me is going to be called height 0. Okay, or z is equal to 0. Okay, so we have a baseline. And anything above this z is going to be positive z. Okay, so we can already tell, for example, that mercury is going to be at a height of 11 centimeters compared to z. Okay, now that's one thing. The other thing I'm going to do is we know that we have to find the pressure gauge at B. So gauge B is right here in the middle. Okay, it's said to be in the center. And we have to find the pressure difference between this and the pressure at A, which is right here. So what we're trying to find is estimate the pressure at A. And we have a pressure at B, at point B, which is completely on the other side, which is equal to 87 kilopascals. And then in between that, we have some different fluids that are different heights for reasons that are, there is probably more pressure in the water than in our gauge B. And that's illustrated by the fact that the mercury is a little bit deeper close to the water. So the mercury is lower at this point than this point, which would generally suggest that the water is going to have a pressure that's greater. So what we can say is from the diagram, PA is going to be greater than PB. That's our first thing. And by knowing that, we're going to see if we get the wrong answer, we can sort of go back and try again. Okay, so the next step is to say, in the same way as before, we're going to find, what we're going to do is we're going to figure out, okay, we have A and B, and we know B, we need to find A. So let's look at the pressure differential between A and B. And we're going to travel along the system from essentially point A to point B from left to right. So I always like to travel from left to right. Some people like to travel always from gauge to the measured system. It really doesn't matter. You just have to follow one technique. So one way, if you went from left to right, you would write PA minus PB. If you went from right to left, you would write PB minus PA. Okay, and the book does the problems a little bit differently as well. So the book does have slightly different solutions as well as I do, but I think my technique is the simplest one to follow. And we can definitely revisit this in a live lecture if needed. Okay, so we go from left to right. So from left to right, we're going to go from A to B. So we're going to say PA minus PB is what we're looking for. And we're going to break it down into different systems. So the first system, which I'm going to draw in orange, is going to be looking at our change in pressure in the water from point A all the way to this change in liquid here, which would be the change to mercury. Okay, and I'm going to call this 0.1. Okay, so I'm going to say the first thing I'm going to do is figure out the difference between PA and P1. So I'm going to write PA minus P1. And I'm going to break it down into that bronze color so we can keep track of it. Now, PA minus P1 is my first step. Now, from there, I know that pressure 1 of water is going to be the same as the pressure 1 of mercury. So what I'm going to say is the next step is I'm going to travel from there up until the system changes again. So I'm going to go in green now. I'm going to go from here, and now we have mercury all the way, and the mercury goes up to here. And I'm going to call this 0.2. So once we reach 0.2, we now have mercury stopping, and we know that we have a difference in pressure between 1 and 2. And we do know from our experience that the difference in pressure between 1 and 2 is the difference in height between 1 and 2. Okay, but our equation is going to take care of that completely by itself. Okay, so we have our next step is to write plus, so we have PA minus P1. Now we're going to have P1, so the first point, minus the second point, P1 minus P2. And I'll put green brackets around that one too so that we have it in green so it follows the color. And the third color I'm going to use is blue. So now we're at 0.2 and we're not yet at the gauge B. We have to go up to gauge B. So we're going to go from 2 to B, and then finally we can get that pressure because we know that in the SAE30 oil, we have a difference in pressure between this level here, the level at 0.2, and the level where gauge B is. Okay, so our third step is to look at the bracket, to look at the third system is to say we have plus P2 minus PB. And if we look at our equation in the same way as before, we could theoretically cancel P1s and P2s and we would be left with PA minus PB. So our equation is correct. We're just breaking down the system into 3 different smaller systems by going from left to right and looking at every time there is a change. So now we can rewrite our equation in terms of our specific weight. So we have negative, we know that PA minus P1 is equal to negative gamma of water multiplied by ZA minus Z1. Okay, I'm just going to write down the equations for all 3. Then P1 minus P2 is gamma of mercury multiplied by Z1 minus Z2. And I did a mistake here. You have to put a negative here, okay? So this is a negative because pressure 1 minus pressure 2 is negative gamma Z1 minus Z2. And finally, negative gamma of oil multiplied by Z2 minus ZB. Okay, so that's our 3 equations for our 3 brackets from the definition of the change in pressure with height when we have a static system. So now we have PA minus PB is equal to some values. So let's put some values in now. So the first value is minus 9,790 multiplied by ZA minus Z1. So what is ZA and what is Z1? So we can see that ZA is from Z equals 0 to the top here. So it's 9 centimeters. So we're going to put ZA is equal to 0.09. Okay, that's in meters. We're going to put everything in meters because that's the SI unit. Minus 0.04 meters. Okay, we see that it's 4 centimeters up until 0.1. So we have minus 0.04. And be careful with your signs. It's very important to keep the signs completely correct here. Okay, then we have minus 133,100 multiplied by, so we know that 0.1 is at 0.04. We already wrote it out earlier. 0.04 meters minus 0.11 meters. Okay, and finally, our last system is the oil, which is 8720 multiplied by, so it's 2 minus b, so it's 11 minus 17. So it's 0.11 minus 0.17. And essentially the level differences are what you're looking for. So if you want to go faster, you can just say, all right, I know my difference between point 2 and point B is 6 centimeters, and I know it's negative 6 centimeters, so let me just write that. But I like to write it out every time so I don't get the sign wrong, because sometimes you think, oh, this is plus 6 centimeters, and it's actually wrong. Okay, so make sure that you do write minus 6 centimeters. So going forward with this, we can now bring PB to the other side, and we can add PB to the left side. So PB we know is, from the question, we know is 87 kilopascals. So PB is equal, so we can add PB to this side, plus 87,000. And if we go through the math of the equation, and I'll let you do that in your own time, we get that PA is equal to 96,350 kilopascals. Okay, and that would be the answer of our example. Okay, so we're going to stop this part 2 lecture right here, and we'll be back for part 3 where we discuss hydrostatic forces on plane surfaces.